Hello. Uh, after uh, after recording the previous video, I found an updated lecture note. So I updated the lecture note last year, and I forgot to use that. So let me just like it's a kind of supplementary video to the previous one. The previous video does not have any problem. I just wanted to use add a few more things. So here is another setup. Actually, it is not another. It's the same setup, but anyhow, let's go. So think about this. Regression model has three types of regressors: x1, x2, x3, and x1 is surely exogenous, x2 is endogenous, but and there is an instrument z2 which is also surely exogenous. But our question is whether x3 is uh, endogenous or exogenous. That is our testing we need to determine. And as a requirement, we have to have enough dimension in the instruments. Then, so even if x3 is endogenous, we should be able to identify the beta. So z2, the dimension of z2 must be greater than or at least equal to the dimension of x2 plus x3. So in this, as you can see, m2, dimension of z2, must be greater than k2 plus k3, so that we can identify the regression without assuming x3's exogeneity. So even if it is not exogenous, still you can identify beta. And null hypothesis is stated this way. So stated this way, and the restriction function can be written as this. It's simple, right? So there and remember the it's k3 dimensional null hypothesis restriction. The null hypothesis has a k3 number of restrictions. So in the end, we know that the test statistic will converge to chi-square distribution with k3 degrees of freedom k3. And in this case, most commonly used test is the Hausman test. Hausman test, depending on textbooks, called Hausman-U test or Durbin-U-Hausman test. Uh, Anyhow, Hausman is the main name, and other, there are some people who had the same idea. So giving credit also to these scholars. So maybe used in different names. Anyhow, let's think about this. Hausman test. Remember, the idea of the Hausman test is to estimate both unrestricted estimator and the restricted estimator. And the key idea of the Hausman test is in calculating the variance. But estimating restricted model and the unrestricted model is pretty simple in this case. Think about the restricted model first. If you use this assumption, if you believe in this hypothesis, then the problem is simple. You only have endogenous variables in x2, so use the instruments only for x2. Instruments is needed only for x2, and x1, x3, no problems. On the other hand, the unrestricted model have endogenous variables in x2 and x3 at the same time. So z2 must be must instrument for x2 and x3 at the same time. It's simple. Both are identifiable, estimable, simple. You know how to do that, and you know how what's their limiting distribution is. So pretty simple. And we know that the test statistic depends on this, the difference between the beta in the unrestricted beta and restricted beta. And the idea was the difference would be zero if the null hypothesis is correct, because both are converging to the true parameter. But if the null hypothesis is wrong, unrestricted model will converge to the true parameter, but the restricted model must suffer from the misspecification bias. So their difference is not going away, but their difference is the bias. This was the idea. Then how can we do this? So we would like to in general we would like to calculate the joint limiting this joint sampling distribution of beta u and beta r if possible, but this is usually not possible, very difficult. So especially the covariance is very difficult to calculate. And if we, by the way, if we knew this, if this was possible, and if we had covariance between unrestricted estimator and the restricted estimator, then you can show that their difference has an asymptotic variance V given by unrestricted models variance plus restricted models variance minus two covariances. That is, so this is correct, and this is, and then you can proceed like this. So this is our result. Okay, this is exactly what we wanted. But here, I will think about two problems, which is already described in the previous lecture. First, covariance is not easy to calculate, but the Hausmann equality simplifies the computation a lot. It simplifies, so you don't need to calculate the covariance in the end, because covariance is the difference between two variances, and then in the end, the variance simplifies to this, right? So this is the final variance. So and calculating variance for the respective estimator is simple, like Stata or like any, like even Excel. I don't know if Excel can handle instruments, but anyhow, say Stata can handle the standard errors. So most statistical softwares can calculate the standard errors, this and this for you, so it is easy to calculate. That is problem number one, which is resolved simply by the clever idea by Hausmann, Jerry Hausmann, and by another problem. Second problem is this. Think about this. The dimension of beta is the coefficient of x1, x2, x3. So the dimension of beta is the total dimension of the total beta is k1 plus k2 plus k3. However, in the end, the degrees of freedom is only k3. So this dimension is k1 plus k2 plus k3. So the variance matrix must be k1 plus k2 plus k3 by k1 plus k2 plus k3 size dimension. Then it cannot be k3 dimension. That's the problem. So it is like mathematically, the problem here is it is larger matrix, but its rank is only k3. So for this to be invariable, its rank must be k1 plus k2 plus k3, but mathematically we can prove that the rank of this guy is only k3 because you are changing only k3 number of restrictions. So restricted model uses k3 more restrictions, so that much is the additional information you are using. So the variance has that much degrees of freedom. This is what I explained here. But in the end, you may resolve this problem by using the generalized inverse of the matrix V. In general, however, that is also right. So to think about this more carefully, if you cannot understand what it means, think about this simple in the simple OLS example. X1, X2 are exogenous. Both are exogenous, but we are testing beta 2 equals to 0 or not. It's like variable selection or statistical significance testing. In this case, the restricted estimator is beta r given by this. So beta 2 is simply 0 because that is the hypothesis. That is the restriction. So this part is simple. But beta 1 is not um, it has to be recalculated, and then its variance matrix will be like this. Of course, there will be no covariance and there is no variance for beta 2 because that part is always 0. In this case, for example, the generalized it is obviously not invertible because it is not full rank. All zeros, 0, 0, 0. In this case, mathematical generalized inverse is defined in this way, right? Like inverting only the part you can. So it is just I'm just giving you a vague idea, rough idea of the generalized inverse and what is the problem, our problem. So also it has the same problem. Our restriction is only about beta 2, but your estimator has larger dimension, right? Restricted estimator has larger dimension, so variance matrix has larger dimension, and that's a problem. You cannot invert this directly. So this much is just a digression to help you understand. And then another solution to this problem is that you can choose you can choose K3 parameters that is going to be used in the test statistic. So we know that we will be testing only K3 number of moment restrictions. And then we are going to take this parameter, right? Like in the end, you need it is usually true, but it is not rigorous. You have to prove that if you want to implement that way. But in general, it holds. So in our case, you do not need to compare. So here I'm comparing unrestricted estimator and the restricted estimator, including beta 1, beta 2, and beta 3. But what I'm suggesting here is using beta 3 only. Compare beta 3 restricted and beta 3 unrestricted. Then it is only K3 dimension, so there is no invariability issue. It is a full rank. Excuse me. Must be full rank, so there is no problem. And this is another alternative. Should be equivalent. This must be equivalent to what we did with full beta. This is another way to avoid the problem and another way to understand what's going on here. And I did not explain this in an earlier. So the reason why you see some kind of inconsistency is because I have updated my lecture note last year, but I did not use that this year. I just found that, so I am kind of using older version and newer version at the same time. So I explained this in the newer lecture note, but did not. So I will let's move on. Skip this. And here you can see maybe more like a more updated, polished lecture notes for Sargon test, over identification test, and exogeneity test. So must be pretty much the same WALT test, Sargon Hansen test. So here I multiplied n now. So it's the same. So I think this part is the same. So if you are willing, you may read it. Okay, thank you for watching, and we'll continue to the next chapter. See you later.